Welcome to DRM1413, Manufacturing Technology, Chapter 4, Sheet Metalworking. This video is prepared by Associate Professor T.S. Dr. Siti Rabiatul Aisha binti Idris from the Faculty of Mechanical and Automotive Engineering Technology. Sheet metalworking is a key area in engineering. We'll provide a diagnostic guide to the mechanics, math, and flaws associated with cutting, bending, and drawing operations. Our content covers an introduction to sheet metalworking, cutting operations including shearing, blanking, punching, and their analysis. We will then examine bending, drawing, and other sheet metalworking operations. Metal forming is classified into bulk deformation and sheet metalworking. Sheet metal constraints include a thickness between 0.4 millimeters and 6.0 millimeters. Operations typically performed cold, yielding high-strength parts with accuracy and a good surface finish. The stamping press involves core components like the punch, sheet stock, and die, producing stampings. Every sheet metal process relies on manipulating the clearance, force, and geometry between a punch and a die. Shearing involves 4 phases: setup, deformation, penetration, and fracture. The cut-edge anatomy reveals the rollover, burnish, fractured zone, and the burr, each related to a phase of shearing. Cutting operations include blanking, which cuts out a part, and punching, which makes a hole. We also have cutoff and parting, slotting, perforating, notching, and fine blanking, each serving a specific goal. Cutting analysis involves calculating the cutting force using shear strength, thickness, and perimeter length. Clearance is critical. Too small causes double burnishing, while too large results in excessive burr. Angular clearance allows scrap slugs to drop freely. The bending stress model manages tension and compression. Compressive stress permanently deforms the shape, while tensile stress is critical for fracture risk, especially if the bend radius is too small relative to thickness. The neutral axis remains unchanged. Bending methodologies include V-bending, where the sheet is pressed between V-angled tools, suitable for low to medium production. Edge bending uses cantilever loading and is for high-volume, complex work, but is limited to bends of 90 degrees or less. Bending analysis includes springback, which is calculated as the difference between the final and punch angles, divided by the punch angle. Bending force is inversely related to the die opening dimension. Drawing mechanics involve 4 phases: setup, bending over the punch and die radii, straightening as the wall is formed, and finally, compression and friction where the flange shrinks. Drawing analysis focuses on feasibility and force. Feasibility constraints include the drawing ratio, reduction, and thickness ratio. Process forces include the maximum drawing force and the holding force, which prevents wrinkling without tearing. Drawing defects include wrinkling in the flange and wall, earring due to material anisotropy, tearing from extreme tensile stress, and surface scratches from inadequate lubrication or rough tooling surfaces. High energy rate forming, or HERF, techniques include explosive forming, electrohydraulic forming, and electromagnetic forming. Each uses different energy sources and transmission mediums for specific manufacturing use cases. The stamp's anatomy involves 3 critical zones: the cut, the bend, and the draw. Poor clearance can cause burrs in the cut. The bend faces tensile stretching, and the draw combines friction and tensile stress, which must be balanced to prevent wall tearing. For shearing, the critical variable is clearance, and failure is due to excessive burrs or high tool wear. For bending, the critical variables are bend radius and springback, with failure being tensile fracture. For deep drawing, friction and blank holder force are critical, and failure includes flange wrinkling or wall tearing. Here is a drawing analysis example. We are asked if forming a cylindrical cup with a 75 millimeters diameter, 50 millimeters height, from a 138 millimeters blank with a 2.4 millimeters thickness is possible. We will use the drawing ratio, reduction, and thickness ratio to determine feasibility. Calculating the drawing ratio results in 1.84. The reduction R is 45.65%. The thickness ratio T/D flat is 1.7%. Since the drawing ratio is less than 2.0, the operation is possible under ideal conditions. This final slide presents a set of exercises covering sheet metalworking operations, differences in cutting operations, types of bending, defining drawing, potential defects, and comparing mechanical versus hydraulic presses.